In the late 1950s, the United States sat comfortably at the peak of the post-war order, with a booming domestic economy, an expanding middle class, and a quiet assumption of absolute military supremacy. That assumption shattered in October 1957. The Soviet Union successfully launched Sputnik, a 23-inch polished metallic sphere with 4 swept-back antennas. It was the world's first artificial satellite, a human-made object placed into a continuous orbit around the Earth. The geopolitical implications were immediate and terrifying to the American public. If a Soviet rocket could carry this small metal ball into orbit, a similar rocket could carry a nuclear warhead across the globe, striking the United States from space and instantly erasing America's geographic isolation. In response to this sudden vulnerability, the U.S. government consolidated its scattered military rocketry, science, and engineering programs. In 1958, they formed NASA, the National Aeronautics and Space Administration, to build a unified, civilian-led counteroffensive. The launch of a single 184-pound satellite pulled the Cold War off the map of Europe and into the vacuum of space, turning a terrestrial standoff into an urgent race to master physics. NASA's immediate hurdle was straightforward but immense. Engineer a vehicle capable of pushing a human being past Earth's atmosphere and bring them back alive before the Soviets claimed the domain of crewed spaceflight. In May 1961, the United States hit its first major human milestone. Astronaut Alan Shepard piloted the Freedom 7 capsule, an extremely compact, bell-shaped spacecraft barely large enough for a single person. This animated diagram shows Shepard's actual flight path. It was a suborbital hop. The rocket generated enough thrust to push the capsule past the boundary of space, arcing up, but lacked forward velocity, so gravity pulled it right back down. The pressure to match Soviet orbital achievements pushed NASA to a critical escalation in early 1962, placing astronaut John Glenn inside the Friendship 7 capsule atop a much larger Atlas rocket. Looking again at the flight path, Glenn's mission had the raw power and velocity to overcome gravity's immediate pull. Instead of falling back to the surface, his trajectory extended into a complete, continuous ring, making him the first American to sustain Earth orbit. Mastering this sustained speed was the mandatory physical prerequisite for the entire space program. Without the physics to survive a continuous orbit around our own planet, there was no bridge to deep space. Pushing past low Earth orbit required a massive leap in both fuel capacity and hardware size, birthing the Apollo program. Engineers designed the Saturn V, a multi-stage super heavy lift launch vehicle, standing 363 feet tall, built specifically to break completely free of Earth's gravity well. In December 1968, the Apollo 8 mission put that colossal hardware to the test, becoming the first crewed spacecraft to leave Earth's orbit entirely. The crew had to navigate across 240,000 miles of deep, irradiated space, execute a precise engine burn behind the moon to enter its orbit, and ensure they had enough fuel to make the return trip. While the engineering math worked perfectly, the mission also delivered an unexpected psychological impact. As the crew emerged from the far side of the moon, they looked backward at their own origin and captured the Earthrise photograph, a bright, fragile marble isolated entirely against the black void of space. Apollo 8 proved that human deep space navigation and multi-day life support systems were fully viable, confirming the moon as a tangible, reachable destination. By the summer of 1969, only one barrier remained. NASA had to transition from circling the moon to actively touching down on its alien surface. The descent of Apollo 11 was intensely complex. As onboard computer alarms blared, Armstrong and Aldrin had to manually navigate their fragile, spider-like lander past hazardous boulder fields to find a safe stretch of cratered ground. They successfully touched down in the Sea of Tranquility. Hours later, they opened the hatch and pressed the first human footprints into the lunar dust. This extraterrestrial feat relied heavily on a vast, unseen terrestrial infrastructure. Thousands of technicians, mathematicians, and engineers sat stationed at complex telemetry consoles in mission control, monitoring every heartbeat, fuel drop, and orbital trajectory. The timeline of this progression is staggering. In a span of just 12 years, humanity went from struggling to launch a 20-inch metallic sphere to landing 2 men on the moon and returning them safely to Earth. The starting gun for this sprint was fired by Cold War fear. But the resulting acceleration in science and engineering permanently expanded our physical horizons, proving exactly what is possible when immense resources are focused on a single, seemingly impossible goal.